Scientists within the U.S. Department of Agriculture and the Center for Watershed Protection have determined a measurable benefit is generated by an urban tree canopy against stormwater collection efforts, air quality control, heat indexes, and power consumption, in addition to just being a beautiful asset for this city to have. The Center for Watershed Protection defines the urban tree canopy as the layer of leaves, branches, and stems which cover the ground when viewed from above. In 2017, Fayetteville's team of GIS staff determined that they'd be able to offer a consistent biannual urban tree canopy assessment utilizing already budgeted resources. My name is Gundar Cody. I'm the GIS analyst who performed this assessment, and I was supported by my peers, Michael Morissette, who's another Fayetteville analyst, and Andrew Machichi, a student from the University of Arkansas. GIS spells out to be Geographic Information Systems. Our work is to process raw and measurable data into information which can be consumed by leaders, guardians, and innovators. We provide quantities, charts, maps, and locational awareness to nearly every department within the city. In this study, I process raw aerial imagery into classified information which gives our leaders a chance at evaluating a notable trend in our tree canopy. I've also created an interface for anyone to explore how our canopy is changing with a change detection web map. This leaf-on multispectral 1-meter resolution imagery was provided at no cost by the USDA's National Agriculture Imagery Program, NAEP. The model I designed was able to identify trees at a 93.8% accuracy. Most of the model confusion occurred between trees and fields, but this model puts an emphasis on identifying the trees in small clusters rather than washing them out with surrounding grasses. I've determined with 95% confidence that the true measure of urban tree canopy within Fayetteville city limits is a whopping 37.4 to 44.6%. That puts us so close to the classic national recommendation of 40% and encourages our urban foresters to continue their efforts at developing and preserving a healthy ecosystem of trees. Currently, we only have around 2.4% of the forest explicitly protected and are seeing a trend of reduction in our figures that's estimated to be at around 100 acres per year via heads-up digitizing. With 2019's imagery on the way, I'm looking forward to applying this model once more and seeing if this trend has been curtailed yet by sapling growth and control measures. When looking at this information, I need to help you understand the many factors that influence these figures and how I am able to maneuver the computer towards an understanding of the imagery. Multispectral imagery is a composition of specific and distinct light wavelengths measured by a sensor and separated into bands. The NAIP provides 4 bands: red, green, blue, and the non-visible near-infrared. The computer classifies the values within a range of 0 to 255. These values indicate the intensity of light reflected from a surface in that color. 0 is negligible, and 255 is the maximum. As you look at these slides, the more colored something is, the more intense was its reflected color. Watch the trees, and you will see they remain dark to gray for every capture. Plants are photosynthetic. They capture light. Man-made objects are not. I wonder if, therefore, an urban canopy is so useful for reducing the heat island effect more than just the shade they cast. Notably, a tree has a low to medium intensity in red, green, and blue, but a significant signature in near-infrared. Water reflects almost no infrared at all, and man-made objects, or disturbed soil, reflect the greatest amount of visible light. Of all measured objects, only plants reflecting more infrared than visible color. A popularized method of separating plants from other objects is to generate a ratio of near-infrared to red. This is called the NDVI, or Normalized Difference Vegetation Index. But this is not enough for this study, because we are interested in separating the grasses and low-lying plants from the trees. Also, I found the NDVI was not refined enough. It was very washed out, and shadows would negate these oh-so-critical ratios I was using. So I needed to generate something which would create a more defined edge in the data. I generated an index from calculations specified in Canadian and British science journals, which I dubbed the Shadow Slayer. It calculates ratios using logarithmic values to reduce the variance in the image and allow a more measurable shadow than I was getting. Finally, a troublesome but extremely important layer I used was a texture index, using a method introduced by Chris Behe in Washington State. This index looks at the range of green and infrared values in a tree-size cluster around every 1 meter square across the city. It generates a ratio from them and highlights clusters of locations that do not have uniformity. Uniformity is easy to see in cut grasses, rooftops, pavements without vehicles. Trees and shrubs show up as bright values among the uniform ratios because their infrared intensity and the shadows they cast. As a GIS analyst, I fed the bands and indexes I generated using Esri's suite of raster tools into an ISO-clustered unsupervised classification. The computer was able to split the 143 million pixels into 40 subgroups which had similar band signatures in about 2 hours of computing. My job was to choose the identity for each of these 40 subgroups among the 5 classes I was creating: tree, shadow, water, grass, and urban. My idea was that shadow is a mixture of other classes, and I would have the neighboring classes nibble out the shadow logically rather than trying to work with the tiny light signatures. Our study in 2012 was performed by Planet Geo, a private company from Colorado which utilized 3 different methods to estimate a 36% tree canopy for our area. They utilized NEIP imagery from 2010, field measurements of growth in selected subdivisions, and iTree canopy. My data covers NAIP images from 2013, 2015, and 2017, using the method I described. What I see is a trend of canopy loss that is significant in that it affects mature trees. New trees take years to grow to a point where they can fight back against the intense light signatures of man-made objects adjacent to them. The young trees planted in the boulevard and planted by themselves surrounded by pavement have a very difficult time getting themselves identified by remote sensing because their light is washed out by the pavement. We will have to wait years for these trees to mature and provide a significant enough canopy that can cover swaths of pavement whole for them to impact our canopy in a positive way. Biodiverse clusters of medium-aged trees and shrubs are the easiest to identify with the methods I used. Looking at this data and comparing it to the accuracy of my model, I'm able to assess that the true value for the urban canopy would vary slightly from my estimation, but it can be considered correct with 95% confidence, which is a significant amount to statisticians. The information is visually verifiable among its peers. Showing imagery from 2017 in the top left, our latest classification in the middle, and the predecessor to the classification in the lower right, it should be visually apparent that my model is able to see more trees than its predecessor. I believe that the values we provide differ significantly because my model is more accommodating and their model is more stringent, even though we are searching for the same things. I created some unique and personalized indexes and methods to help identify troublesome trees, and the results are striking. Best of all, Fayetteville now has a documented and duplicatable method of determining tree canopy at minimal cost to the taxpayer. We can afford to assess our canopy at the same rate as images are generated by the USDA, and we can identify change by comparing years against each other. Areas of red, we have displaced trees for urban development. Areas of yellow will more commonly be caused by camera angle and other numerous factors, but sometimes represent trees and shrubs being cut down for open field. Blue is more of that camera angle and shadow problem, but also shows something that was urban may be covered by tree growth. And green shows where a field slowly begins to be receded by trees and saplings or covered by growth. Planet Geo set the groundwork for how we understand our canopy and how we can put a number on its value. Their science is sound, and their research gave us the framework for the foresters to establish their goals. Our new model is here to stay and gives us a unique way of measuring our progress every step of the way. You can explore our Canopy change for yourself by visiting the web map we've created in link 3. A training video was posted to Fayetteville's YouTube to show you how to utilize this web map in link 2. Link 1 may help you understand more of how we put the piece together.